Hello, in this notebook, we are going to cover four advanced Keras customization techniques that go beyond what the standard API gives you out of the box. A custom learning rate scheduler built as a Keras callback, a Monte Carlo variant of alpha dropout, a custom dense layer with max norm weight constraint, and a fully featured tensorboard integration that logs metrics you would never get from the default callback. First and second cell consist of setup and data. We import TensorFlow, Keras, PyTorch, NumPy, and Matplotlib, then load Fashion MNIST 10 classes of clothing images at 28 by 28 pixels. Fashion MNIST is used instead of CIFAR10 here because it is a clean enough to see training dynamics clearly without requiring a very deep network, and all four topics in this notebooks are about training dynamics rather than raw accuracy. Moving ahead, we have custom learning rate scheduler. Starting with one cycle scheduler, the theory cell explains the one cycle policy proposed by Lacey Smith in 2018. Instead of keeping the learning rate fixed or decaying it monotonically, the policy has two phases. In the first phase, the learning rate rises linearly from a very small value up to a peak. In the second phase, it falls via a cosine curve back to an even smaller value. The intuition is that the high LR phase acts as a regularizer. It forces the optimizer to escape sharp minima and find flatter, more generalizable regions of the loss surface. Moving forward, we implemented this as a one cycle scheduler class that's subclasses keras.callbacks.callback that has been defined here. On each batch, we compute the current step position within the total schedule and update optimizer.learning rate accordingly. Visualization is plotted before training so you can see the characteristic ramp up and cosine cool down shape. We then run on A/B test one model trained with a constant learning rate and one with the one cycle schedule, both for the same number of epochs. The one cycle model converges faster and ends with higher validation accuracy. The PyTorch version uses PyTorch's built-in torch.optim LR scheduler.oneCycle LR, confirming the same pattern holds in both frameworks. Next we have this is all about the one cycle LR versus constant LR. You can see the value accuracy curves here. The PyTorch one cycle that I have just mentioned. Then comes the custom dropout, Monte Carlo alpha dropout. The theory cell distinguishes alpha dropout from scratch dropout. Standard dropout shifts the mean of the activations with its zero neurons, which is a problem of CELU-based self-normalizing networks. Alpha dropout was specifically designed to preserve the mean and variance of the input, making it compatible with CELU. Our MC alpha dropout class subclasses Keras built-in alpha dropout and overrides a single line. The call method always passes training is equals to 2, true to the parent, regardless of what the outer model is told. This means dropout is permanently active, turning every forward pass at inference time into a stochastic sample from the approximate posterior. We then run 100 forward passes on a test batch and collect the mean and standard deviation across those passes. The output confirms the key property. The model reports higher uncertainty on the sample it gets wrong than the sample it gets right, meaning the uncertainty scores are actually informative. Next, we have max norm dense. Max norm regularization, originally proposed by Hilton in 2012, constrains the L2 norm of each neuron's incoming weight vector to never exceed a maximum value. Crucially, unlike L2 weight decay, it does not shrink weights that are already small. It only clips weight that have grown too large. We implement this as a max norm dense custom layer that subclasses keras.layers.layer. After defining the weight tensor with add weight, we override the call method to apply the norm clipping after every forward pass using tf.clip_by_norm. This prevents any single neuron from dominating the network's representations regardless of how long training runs. Next, we have tensorboard integration. The theory cell lists the 5 tensorboard dashboards we will populate. Scalars for loss and accuracy, histograms for weight distributions, the graph view for architecture visualization, and images panel and custom scalars. We write an advanced DB logger callback that goes far beyond the standard tensorboard callback. On each epoch, it logs the current learning rate, the L2 norm of every weight tensor across all layers, and the gap between training and validation accuracy, a direct measure of overfitting. After training, the standard percent tensorboard magic launches the dashboard inline in colab. You can see that here. The PyTorch section replaces this with a summary writer that logs scalar metrics and histograms after every epoch using the same log directory convention. So both TF and PyTorch runs can be compared side by side in single tensorboard instance. You can see that here. To summarize, the final summary cell prints the validation accuracy for every experiment in the notebook. The one-cycle schedule outperforms the constant LR baseline. The MC alpha dropout model produces calibrated uncertainty scores, max norm dense train stability without any explicit learning rate tuning, and the tensor board has a full set of custom diagnostic ready for inspection. This was all about this collab. Thank you for this.